Welcome back to Mastering Algorithms. In previous episode, we learned what time complexity is and why it's important. We also compared linear search and binary search. But here is a question that every beginner asks. I understand big O, but how do I actually calculate it when I see code? That's exactly what we will learn today. By end of this video, you will be able to look at a piece of code and confidently determine its time complexity. We will start with simple examples and gradually move to slightly more complex ones. Many beginners believe shorter code is always faster, but that's not true. Let's imagine two programs. The first program has only 5 lines of code. The second has 20 lines. Can we say the first one is faster? No. The number of lines has almost nothing to do with performance. What matters is how many operations are performed as the input grows. That's why we analyze loops, recursion, and repeated work, not the length of the code. Let's start with a simple example. We initialize the variable sum once. Then we enter the loop. Suppose n equals 5. The loop runs 5 times. Inside each iteration, one addition is performed. If n becomes 100, the loop runs 100 times. If n becomes 1 million, it runs 1 million times. Notice something important. The work grows exactly in proportion to n. When the input doubles, the work roughly doubles. This is O of n. How many times does the main operation execute? We should always remember this question. It is a useful tip. We should always ask ourselves for any code how many times the main operation is being executed. And that question will solve most of our problems while calculating time complexity. Now, let's look at another example. Here we are accessing a single array element. Does it matter whether the array contains 10 elements or 1 million? No. The computer directly jumps to the required index. It performs essentially the same amount of work every time. That's called constant time or O of 1. The important thing isn't the size of the array. The important thing is that the work doesn't grow with the input. Here is another common example. There is one loop. It starts at 0 and ends at n. So if n is 10, the loop runs 10 times. If n becomes 1000, it runs 1000 times. The number of operations grows linearly. Therefore, the time complexity is O of n. A simple rule to remember is one loop usually means O of n. Of course, there are exceptions, but this rule works for many beginner problems. Now things become more interesting. We have a loop inside another loop. Let's assume n is 3. The outer loop runs 3 times. For every iteration of the outer loop, the inner loop also runs 3 times. So the total work is 3 multiplied by 3, which is 9. Now suppose n becomes 100. The outer loop runs 100 times. Each of those iterations executes another 100 operations, the inner loop. That becomes 10,000 operations, 100 into 100. In general, n multiplied by n equals n square. That's why nested loops usually have O of n square time complexity. This is why algorithms like bubble sort become slow for large data sets. Many people think two loops automatically mean O of n square, but that's not always true. Notice something. These loops are not inside each other. The first loop finishes completely, only then does the second loop begin. If the first loop runs n times, the second also runs n times. The total work is n plus 1, that is equal to 2 into n. In big O notation, we ignore constant multipliers like here is 2. So 2n simply becomes O of n. This is one of the most common interview tricks. Always check whether loops are nested or consecutive. Here is one of the most confusing parts of big O. Why do we ignore constants? Imagine two algorithms. One performs 2n operations, the other performs 100n operations. Yes, the second algorithm is slower, but as the input grows, both increase at exactly the same rate. Big O focuses on the growth pattern, not the exact count. Similarly, O of n plus 20 is still O of n because those extra 20 operations don't become more significant as the input grows. Think of big O as looking at the bigger picture. Let's look at another example. Suppose an algorithm performs n square operations and later performs another n operations. Which part grows faster? The quadratic part. When n becomes very large, the n square term completely dominates the linear term. For example, if n is equal to 10, then n square equal to 100. The quadratic part is already much larger. If n is equal to 1000, then n square becomes 1 million, while n is still only 1000. That's why we keep only the fastest growing term. So O of n square plus n becomes simply O of n square. Let's quickly test what you have learned. Take a few seconds and think about the complexity of each example before looking at the answer. The first example has one loop, that's O of n. The second contains nested loops, that's O of n square. The third performs a direct array access, that's O of 1. If you answered all three correctly, you are already thinking like an algorithm designer. Whenever you analyze code during an interview, follow these four simple steps. First, count how many times the important operation repeats. Second, ignore constant values. Third, keep only the highest growing term. Finally, check carefully for nested loops, recursion, or repeated work. If you follow this process, you will solve most beginner and intermediate time complexity questions with confidence. Now you know how to calculate time complexity. But algorithms don't just use time, they also consume memory. Sometimes a faster algorithm uses more memory. Sometimes a slower one saves memory. So, how do we decide which is better? That's exactly what we will explore in the next episode, where we will learn space complexity with practical examples. If this video made Big O easier to understand, please like the video and subscribe to the channel. In the comments, tell me which concept you found most challenging. In next episode, we will explore space complexity, another essential topic for coding interviews and writing efficient software. Thanks for watching and I'll see you in next episode.